Hello everyone, welcome to my channel. Today we are going to look at ESP32, an inexpensive and easy-to-use microcontroller that is ideal for your next project. Let's get started. First, what is an ESP32? The ESP32 is a low-cost, low-power system-on-chip SOS microcontroller with built-in Wi-Fi and Bluetooth. It was developed by Espressif Systems, a Chinese Fables' semiconductor company, and it has become very popular for its low-cost, low-power consumption. In wide range of applications including IoT, biomedical devices, home automation, robotics, and wearable health systems. Next, let's look at some of its features. The ESP32 has a dual-core Tensilica microprocessor, which is a 32-bit up to 240 MHz processor. It comes with built-in Wi-Fi 802.11b GN and Bluetooth version 4.2, which is both classic and BL. On the memory side, it has about 520 kilobytes of SRAM and 448 kilobytes of ROM and 4 megabytes of flash. Most development boards have this amount of flash, but it can be expanded up to 16 megabytes if needed. The ESP32 also has around 34 general-purpose input-output pins, GPIOs, depending on the module or board you are using. These GPIOs support PWM, ADC, DAC, IYC, SPI, UART, CAN, and touch sensors. Additionally, it has other features such as a 12-bit ADC with up to 18 channels, 2 8-bit DAC, a built-in Hall sensor, and capacitive touch sensors, which are ideal for biomedical applications where you need a UI. Next, let's take a look at the different types of ESP32 development boards. The chip itself comes in different modules like the ESP32 room, ESP32 room, ESP32 room. But to use it, you will need a board that has the USB, a voltage regulator, and pins to interface your circuit. Some of the most common boards are the ESP32, DevKit V1, the ESP32WROOM32, the ESP32 Rover, which has extra RAM for really heavy tasks like image processing, and newer versions like the ESP32S2, ESP32S3, which come with USB OTG and better AI acceleration, and the ESP32C3, which has a RISC-V core and is ultra-low power. Alright, next, let's quickly go through the pin functions. We have GPIOs, which are general-purpose input-output pins. ADCs, which is the analog-to-digital converter used for sensors like temperature. ECG and SPO. We have the DAC, which is the digital-to analog converter used for generating analog output. The UART pins are used for serial communication like with the EG module, 88232, and other sensors. The SPI and IYC pins are used for interfacing sensors like the MAX30102, old displays, and so on. The PWM pins are used for controlling servo motors, LEDs, etc. And finally, we have the touch pins, which are used for capacitive touch sensing. Alright, now let's talk about how to program the ESP32. You can program the ESP32 using the Arduino IDE, which is great for beginners because there are a lot of biomedical sensor libraries available. You can also use the ESP-IDF, which is the official SDK for developing IoT applications. If you want to run Python directly on the ESP32, then you can use MicroPython. And lastly, you can use Platform Yo, which is an advanced development environment. Alright, next, let's discuss power management. This is very important, especially when you are making wearables. In active mode, the ESP32 draws about 160 to 260 milliamps, and this goes down to less than 10 microamps in deep sleep mode, which is perfect for battery-powered biomedical devices. The ESP32 is powered by a 3.3V regulator, so you need to supply it with a 3.3V logic level. Most commonly, it is supplied from a 5V USB, and you can easily make it work with batteries like the Lion or Lepo 18,650 cells, and you can add a charging circuit as well. Finally, let's take a look at some applications. In general, it can be used for IoT smart home devices, wearables, and fitness trackers, robotics and automation, wireless data logging, and industrial monitoring. In biomedical engineering, it can be used for ECG monitoring using the 88232 module and sending the data to a mobile app, pulse oximetry. SpO2 plus heart rate monitoring with the MAX30102 sensor, body temperature monitoring with the LM35 or DS18B20 sensors, and creating a wireless patient monitoring system where you can send all the data gathered by the sensors to a phone or cloud over Wi-Fi or Bluetooth. Other applications include smart prosthetics and bionics, where the ESP32 can control the actuators and motors and at the same time send feedback to the user. We can also use it for remote data logging, where you can upload patient data to the cloud using Firebase, ThingSpeak, and other similar services. Now let's take a look at some of the advantages of using an ESP32. First, it is cheap. Costing only about $5 to $10, it has built-in Wi-Fi and Bluetooth, which eliminates the need for additional modules. There is a huge community and many ready-made libraries available. It supports IoT cloud integration and has low power modes which allow it to operate on batteries. Now let's take a look at some of its limitations. First, it needs a 3.3V logic level and is not 5V tolerant. The ADC accuracy is not as high as dedicated ADC chips. You need to design the power supply properly because the ESP32 can draw spikes of more than 500 milliamps during Wi-Fi transmitting. Lastly, for very simple tasks, you might find it overkill, and in those cases, you can use the ESP8266 or the Arduino Uno. In summary, the ESP32 is a powerful, inexpensive, and easy-to-use IoT microcontroller with built-in Wi-Fi and Bluetooth. It is ideal for biomedical engineering projects such as wireless ECG and SPO2 monitors, smart prosthetics, wearable health devices, and IoT-enabled health devices. If you want to learn more about the ESP32 or related technologies, check out the links below. Thanks for watching, and see you in the next video.